And it says that I'm live. I really hope that this works. Because again, the live chat on my Chromebook is not loading right there. But I can see the live chat on a mobile device. So just so you guys know, in the live chat right there, I got to try to hold up the camera to it. I do have the live chat right there. So if you do comment, I should be able to see that on my phone, and it will be saved to the video. So I should be able to get an accurate attendance from that. Yes, we're back. We're back. My word, 3-day weekend. Oh, goodness gracious. You ever wonder what teachers do during a PD? No? Okay, great. You do wonder. What do you think we do? It's mostly meaningless stuff. Yeah. Yesterday, we learned something about something brain learning. I don't know. I really don't know. I got my work done. Is what I did. But regardless, we'll figure that out. For those of you in the live chat, if you would leave a comment, just because, again, I'm looking at my phone, I just want to make sure that it works properly. I'll be checking on that just in case I don't see any comments. As for today, you did have a homework due for me. I'm just looking at that right here. Yep, it was due right there at 7:20. It looks like about half the people turned that in. So, there you go. There comes some comments. So now I know that the comments actually do work. So good. My objective for today is to go through some of those problems from the homework that y'all turned into me. Now, again, I emphasized the way that I worded the assignment. I said the following homework problems are to be completed, blah, 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 blah. I would like to review these problems with you on Tuesday in preparation for an assessment next week. When I say next week, that is now currently this week. Said email me with any questions. Remember, this is a homework not graded on correctness. Simply because I wanted to be able to try these problems together. So I have a few in mind that I definitely want to hit up. So what I'm going to suggest that you do is this. Number one, if you do have the physical papers of the work that you did, definitely have that out ready to compare against what we're about to go over. But I would also suggest that any vital piece of information that we kind of go over or review or talk about or insight that you receive, you do write down in a safe and secure location. Oh, I don't know, maybe a notebook. Maybe have those notebooks out and open. Because again, this is part of a review towards an assessment that we are going to be taking later this week. Ha 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 ha. Moving over here. There we go. I can bring up my Pearson textbook, online textbook. There we go. Flip the screen over. Boom. And this thing will launch. Come on. Okay, that's really zoomed in. Page. Good. Okay. So there was some of these problems that I went over on my own in preparation for this class period. And I had thought to myself, like, oh, these are perfect. These are the types of problems where they're really getting into the minutia of assumptions and conditions and whether or not it is appropriate to move forward with a certain piece of information. The first two problems that I would definitely like to go over, I would definitely like to talk about number 12. Let's see. And I think it was that one. Which one was the one about UC Berkeley? Was that number 16? But okay. Because if that's the one about UC Berkeley, then I definitely want to talk about that one next. Yes, it was. Haha. That's great. Remember when we looked up the hotel remember when he looked up the hotel last week? Yeah. I followed your advice for the UC Berkeley one. I Google searched how many people actually apply to the UC Berkeley School of Business. It technically violates the 10% rule. I know. It's like, what? I know, but we'll talk about that. But first, I want to talk about number 12. So let me zoom in on number 12 a little bit. Actually, before I do that, I want to load up this one. There we go. Cool. I'll load up this one just so I have it for my calculator. There we go. Okay. Make sure the people in the chat can see that. Again, for those of you in the chat, if you haven't left a comment, please leave a comment. I can see them right here on my phone. But definitely, if you can't see the words, this is your online textbook, page 659, number 12. And again, whatever problems that we don't go over where you're like, ooh, I wish I could have seen that one, please let me know when we're done with these. But these are the ones I want to go over first. Number 12, a study of auto safety determined the number of driver deaths per million vehicle sales, classified by type of vehicle. The data below are for 6 mid-size models and 6 SUVs. Wondering if there is evidence that drivers of SUVs are safer, we hope to create a 95% confidence interval for the difference in driver death rates for the 2 types of vehicles. Now, they're not actually asking you to do that. They are not actually asking for you to create the interval. What they are really way more interested in are these data appropriate for this inference. Now, even though they don't say it, it all comes down to assumptions and conditions. This problem is all about assumptions and conditions. We have to talk about the assumptions and conditions in order to say whether or not it's appropriate for this inference. Now, first and foremost, if I'm looking at the type of data that I have 2 samples, and they're talking about death rates. I'm assuming, oh, there it is, deaths per million. So this is not a percentage. This is not categorical data per se. I mean, I could technically average these numbers together, and it would make sense. So this is quantitative data. I do not have a population standard deviation, so it looks like I would be running for t-testing or t-intervals or what have you. For t-testing or t-intervals, we definitely we don't have to have a large enough sample size. We don't have to, but it would potentially be helpful. I'll talk about why that is in a moment. But we need to make sure it doesn't violate the 10% rule. We need to make sure that there was randomness. Randomness could then imply or inform independence, which we can talk about. But more importantly, we need to hit the nearly normal condition. The data needs to be distributed in a nearly normal fashion. Now, there are only 6 data points, but we'll deal with that in a minute. What I did with this problem, what I wrote down, I said, okay, I think it's reasonable to say that both samples were independent of each other. So I wrote something along the lines of that. What did I write here? Between the SUV models and the mid-size models, I decided, I'm like, okay, well, what's a brand of SUV? Name? Do you know? Okay, I don't know. Cool. But if brand SUV A, or you know, if this was like some SUV model A and this is some SUV model B, my point being though is that the individual statistics don't affect each other per se. You can't say that like, you know, well, model A affected the number of deaths in model B. I'm talking about independence between everything. Reasonably independence. They don't really talk about the randomness. They don't talk about the randomness whatsoever. I don't know how many SUV models or mid-size SUV models are actually out there. Let me actually just kind of Google this real quick. Maybe they took a census. I don't know. How many SUV models on the road? Question mark. Okay, that did not help. List. Okay, sport. Okay, list of sport utility vehicles. All right. Oh, that's a lot. That is a lot. I'm only up to the C's. Holy crap. Okay. So they looked at 6, but they don't say how those 6 were found. I don't know whether or not this could be classified as random. I don't know. I don't know. Not to mention, there are some SUV models that are way more popular than others. So it's like, what if there's one type of SUV that there's just a lot more of them on the road and have more chances at well, taking people's lives? I don't know. That's interesting, because they did scale it to deaths per million vehicle sales. Yeah, I can't really talk about randomness. Well, can't talk about randomness. I talked a bit about independence. Well, I'm going to type this data into my calculator. I'm going to flip my camera over so that we can check the nearly normal condition. Okay, 47, 54, 64, 76. I'm just double checking, make sure that my numbers are correct. Cool. Flip this over. Zoom that sucker in. Let's take a look at some histograms, see if this thing is nearly normal. And then we can come to an ultimate conclusion here. Oh, plot 1. Oh, change it to L1. There we go. Zoom 9. Huh. There were 6 data points. Oh, man. Yeah, so I mean, it looks skewed to the right. But the only way that I would be able to forgive if it was skewed to the right is if I had a large enough sample size, which we don't have. There's only 6. Let me look at L2. Let me look at L2, the other type of cars. Oh, holy crap. Yeah. I can't meet the nearly normal condition. I cannot meet the nearly normal condition. They didn't speak to randomness. This clearly doesn't meet the nearly normal condition. The only way that I could forgive the nearly normal condition is if the sample size was large enough. I cannot in good conscience move forward with inference or intervals or anything along those lines. It says, are these data appropriate for this inference? No, they are not. Why? Explain. Well, randomness was never spoken of, and there's nothing indicating that there's any reasonable form of randomness, not to mention that the data, when plotted in a histogram, is, well, skewed to the right, and the sample size is not large enough to forgive that. So, this data is not appropriate. Cool. Let's talk about UC Berkeley. Boom. Somebody Google this for me so I don't have to bring it up while I read this. But somebody Google how many applicants to Haas School of Business, UC Berkeley. How many applicants? Haas School of Business, UC Berkeley. And you Google that while I read the question. In September of 2002, CNN reported on a method of grad student recruiting by the Haas School of Business at UC Berkeley. The school notifies applicants by formal letter that they have been admitted. Yay! And also emails the accepted student a link to a website that greets them with personalized balloon cheering and applause. Are you guys too young to remember Evites? You are? What do you think an Evite is? Yeah. You could send like e-cards. Everything was E back in the day. I don't know why. Electronic? Okay, maybe why. I figured it out. Anyway, back to this. The director of admissions says this extra effort at recruiting has really worked well. The school accepts 500 applicants each year, and the percentage that actually choose to enroll at Berkeley increased from 52% the year before the web greeting to 54% this year. It says to create a 95% confidence interval for the change in enrollment rates, which we will. And then it says, based on the confidence interval, are you convinced that this new form of recruiting has been effective? That actually would be very kind of easy to kind of talk about, let's say. I want to write out a couple things here for this problem. They want me to perform a confidence interval. They want a 95% confidence interval. Just going to putting these into my notes right here so I'm just labeling it. There we go. Boom. And I'll flip my thing over in a moment. Zoom out. There it is. They want a 95% confidence interval. Now, there is no expected percentage. However, I could say something along these lines. I could say that, 500 and 500, because this is from 1 year to the next, 500 1 year, 500 the second year, are large enough samples. They definitely are. Now, this is going to be a little weird, but I could do something like this. I'll zoom in a little bit on that. There we go. I already did the calculate. No, I didn't do the calculations for these. Whatever, I'll check them in a moment. What am I checking right now? What exactly am I checking right now? Cricket. A lot of people just want to say, oh, successes and failures. Yes, I know, but more specifically, what type of successes and failures? There's technically two types of successes and failures that you could speak to. Say again? Well, that's the thing, though. We can't do expected because we're not. I almost dropped that. We can't do expected because we're not. We don't have an assumed null hypothesis per se, or we don't have an assumed percentage. So these are observed. When you don't have, and this is very important for when you do one sample proportion stuff, when you don't have an assumed population mean, when you don't have an assumed population proportion, then you have to go with what's observed. But if you are assuming a certain proportion, then those would be expected. But these are observed. And I say they're observed because they're literally from the two samples right here. It says that 1 year, they accept 500 applicants each year. 1 year, the 52% chose to enroll, and then the next year, 54% chose to enroll. Two independent samples from each other. So I'm just going to abbreviate OBS for observed. Again, assumptions and conditions, they can be tedious, but you got to get used to that kind of stuff because they're going to rack you on that. Now, this is where it gets a little weird. Randomness. The problem doesn't really talk about randomness, but there is a reasonable randomness inherent in the problem. There is a reasonable randomness inherent in the problem. If the sample size is 500, one could argue that those 500 applicants from 1 year to the next are quote unquote randomly selected. It gets a little dicey because it's like, well, could you really argue that they're random since they're getting accepted to the School of Business at UC Berkeley? Is it really random, or are these the most qualified? And then, okay, they accept 500 people, but then of those 500 people, not all of them choose to enroll. It gets a little dicey. So one thing we can speak to is this. You could say independence of getting acceptance letter is reasonable. You could speak to the independence, which would then ultimately inform the randomness. Because if I'm getting an acceptance letter to the School of Business and you're getting an acceptance letter to the School of Business, My getting my letter does not affect whether or not you are getting your letter. So it is acceptable to talk about that level of independence. You could even say independence of both years of recruits is also reasonable. Meaning from one person to the next, you could talk about the independence, but also from one sample to the next, you could talk about the independence. Again, randomness, it gets a little dicey talking about randomness. Can't just be like, yep, it's random. Well, you got to look into the context of the problem. The context of the problem. So I'm going to write something like, randomness, if I can spell randomness today. Randomness is not explicit, but we will proceed with interval. Anybody look up the enrollment for UC Berkeley? What was it? Oh, yeah, because we're talking about applicants, right? Yeah. But is that how many people enroll? Applied. Yes. Okay. Now that's the key, though. How many people applied? You said it was about 3,600. 10% would be 360. The problem never speaks to it. The problem in the back of the textbook, and well, in the back of my textbook, it says basically, it says something basically along the lines of, yeah, the 10% rule is met. We can assume that there's, over 5,000 people applying. No, there's not. What? But again, it's like we're really splitting hairs at that point. We're really splitting hairs. In reality, I'm just going to write something like this. 500, less than 10% of applicants is reasonable. Here's the thing. You are not going to be Googling a statistic like that in the middle of the AP test. You're clearly not. You have to use common sense and logic. 5, is it reasonable to think that maybe 5,000 people applied? Oh, according to my Google search, it was 3,600. Okay, but we're splitting hairs. We're literally splitting hairs at that point. Gosh. It's reasonable. And I'm going to go with that. This weird thing. So I'm going to run here it is, the 2 prop Z interval. Since we're dealing with categorical data, that's a test. I want an interval. The 2 prop Z interval. Oh, I already threw my data in. Now, this is 500 and this is 500. Now look at the order that I put them in. Look at the order that I put them in. Let me get rid of that. I put 0.54 times 500. On my calculator, it actually just automatically calculated to 270, which is nice. It does. Cool. But I believe that 270 number, that 0.54 times 500, the 54% represented this year. So just something to keep in mind. I prefer, myself personally, I prefer to put the larger percentage in first, or the larger count in first, let's say. You don't have to do it that way. If you do it the other way, you'll still get an appropriate answer. You will get an appropriate answer. But I decided to do it this way because I like it better. Looking at the difference between the two. It was 95%. Yes, 95% confidence. Boom. There's my interval. My interval is from approximately negative 0.042, comma 0.082. But then the question is, mind you, it doesn't say to interpret. It says to create the interval. It doesn't say to interpret. But if you had to interpret, you could say that you are 95% confident that the true difference in enrollment rate, I guess you could call it, the true difference in enrollment rate from this year to last year is within this interval. But the real question is this. Based on that interval, are you convinced that this new form of recruiting has been effective? No. As many of you have probably already figured out, no. I am not convinced that it's effective because 0 is in the interval. And because 0 is in the interval, there is a possibility that the true difference in proportion is 0. Just simply put. Let me see what happens if I reverse it. Check this out. Watch what happens if I reverse it. You always like to see the other side of this too. If I put, instead of 270, 260, I put 260, 270. Watch what happens. Watch what happens. I just wanted to show you that even if you do reverse them, you basically get a mirror interval. It's a mirror interval. Now I'm 95% confident that the true difference in enrollment rate from last year to this year is within this interval. Are you convinced? No, I'm not convinced because 0 is in the interval. So it doesn't matter which one you do. Just as long as you explain it out in words, you should be fine. Okay. Let me see what we got here. Oh, that's fun. Okay. Number 28 is the gold standard of today. But before we get to number 28, because I would like to spend a good deal of time on number 28. Before we get to number 28, is there a problem on the rest of the homework that you would like to see very briefly? Like, because I think we did either number 10, number 24, or number 40. Because otherwise, number 28, like I said, is the gold standard. That's the one that I'm going to be spending the most time on today. Were you all thinking number 28 when we came in? Okay, cool. Question. Anybody have a p-value for me from number 28? A p-value that I would like to either, what's the word I'm looking for? Confirm or deny whether or not that was the p-value that you wanted. Everybody get it? What'd you get? 0.119. What was your alternate hypothesis? Okay. I think I know where 0.119. You said 0.119. That was it? 97? Yeah. For your alternate hypothesis, I think you left it at not equal to. Yeah, because the p-value that I got is exactly half of that number. Did I write it down? I don't think I wrote it down, but we're going to talk about that within the problem itself because that has to do with the context. Yeah. Why didn't I write it down? I was just jotting down notes for myself. But yeah, it should be exactly half that. In fact, I did it right here. There's your p-value divided by 2. In fact, the one that I got was literally that. It was 0.0598 is what I wrote down. 0.0598. That was the p-value. Now, here's the issue with 0.0. I'll leave this up here. Here's the issue that you're going to potentially run into with a p-value like that. You're going to have to talk about it in your conclusion. The fact that, well, the threshold's 0.05. The threshold's 0.05. So we would fail to reject. Yeah, but it's so close. It's so close. And you're the one who's arbitrarily putting your p-value at not p-value, your alpha at 0.05. Ooh, we're going to talk about that. Oh, it's going to be fun. And we're going to talk about type errors. This is an amazing problem. Number 28 is exactly the type of problem that they would throw at you on an AP test, which is why I want to spend most of our time with this. Oh my goodness, number 28. Let's go to number 28. How do I go to number 28? Am I zoomed in too much? Yep, I am. Number 28. There we go. Ha ha ha. Okay. Several programs attempt to address the shortage of qualified teachers by placing uncertified instructors in schools with acute needs, often in inner cities. A 1999 to 2000 study was taught by certified teachers to others taught by uncertified teachers in the same schools. Reading scores of the students of certified teachers averaged 35.62, standard deviation of 9.31. The students instructed by uncertified teachers had a mean of 32.48, clearly less, with a standard deviation of 9.43 on the same test. There were 44 students in each group. And then they even give you this interesting piece of information, which I'm going to talk about where this came from. Although on the computer screen, I can see literally right now, there's just the giant glare right there. That's okay. The appropriate T procedure has 86 degrees of freedom. Where did they get that? We'll talk about that. I'm going to show you where they got it. Is there evidence of lower scores with uncertified teachers? Discuss. It's interesting. They're talking about often inner cities. My wife did her student teaching when she was in college. She did her student teaching in Newark. And she told me about just, again, the same thing. This was in 2000, I want to say it was 2008. But she talked about the shortage of teachers, like the shortage of like good teachers. They have qualified teachers. They just don't have like good teachers because not a lot of people want to go and teach in certain areas like the inner city. In fact, it's really the inner city and it's really like super rural America, like super rural America. Think about a town that might have like 50 people living in it or something like that. Nobody wants to go out to teach to a town of like 50 people in the same way that no one really wants to go. I shouldn't say no one. There are people who do want to do that, but not as many people want to go into the inner cities. So what they do is they get these uncertified people to go in to these places and teach for a set number of years. And they say, okay, we'll pay you this much. And it's like a lot more. Most of the time, we'll pay you this much to work for 3 years, and then after that, we'll reassess. And then after those 3 years, they're just like, yeah, see ya. Most of the time. It's not fair. It's really not fair, but it's what happens. But let's talk about this. There's a lot of information floating around on this problem. I need to organize it. First and foremost, I want to organize it. Yes, we're going to be talking about a hypothesis test. Yes, this is going to be a T test, more specifically a 2-sample t-test. Not a paired one, but a 2-sample one. So let me write down some information on my page here. So first, this is number 28. I'm going to organize it like this. X bar sub C is equal to 35.62. And S sub C is equal to 9.31. It's important to differentiate your sample mean and sample standard deviation. So I'm doing a little subscript. You could choose anything you want. You could do sub 1, but I'm doing sub C for certified teacher. And X bar sub U is equal to 32.48. And S sub U is equal to 9.43. Again, the U indicating the uncertified teacher. Both sample sizes are 44. But again, according to the problem itself, and we're going to have to talk about this with assumptions and conditions. We're going to have to talk about this, but I guess it can be assumed that each class was independent of each other. It can also be reasonable that when students were enrolled in one class or the other, that there was a random selection. I don't think that they put all of the smart students in one class and all of the not as smart students in the other class. That would clearly mess up this experiment. I get, it is reasonable, even though they don't say it. Several programs, blah, 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 blah. Reading scores, certified teachers, blah, 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 the 44 students in each group. Yeah, they don't say it, but it is reasonable to say that, students were randomly placed in each class according to enrollment standards. But they want to know, and I go back to the question here, is there evidence of lower scores with uncertified teachers? Is there evidence of lower scores with uncertified teachers? That question will inform our hypotheses. H sub 0. I have to use population parameter stuff in here. The null hypothesis is that there is no difference. The null hypothesis is that there's nothing going on. Nothing to see here. There's no difference between the two. My null hypothesis. My alternate hypothesis is informing what symbol goes in place of the equal sign. And because the question is talking about, is there evidence that the uncertified teachers produce lower scores, that informs this as my alternate hypothesis. If the uncertified teachers are producing lower scores, which is technically where my evidence is pointing to, then it's got to be greater than for the alternate. If the question instead said, is there evidence of a difference between certified and uncertified, then yes, I would do not equals to. But this just said specifically, is there evidence of lower scores with uncertified teachers? This is the proper interpretation of those hypotheses. Proper interpretation. Let's talk about assumptions and conditions, because again, the 4 steps. Number 1, state your hypotheses. Number 2, assumptions and conditions. Number 3, perform the test. Number 4, state your conclusion. Let's talk about assumptions and conditions. There we go. So let's see. First of all, randomness of assigning students to class is reasonable. Again, I'm putting it into context. I'm not just saying, yep, randomness. Yep, check. No. You cannot just write the word randomness and hope that it works. You cannot write the word independence and hope that it works. Put it into the context of the problem. And notice, I'm not saying that it was stated in the problem. I said that it's reasonable. You could also say independence of individual scores is reasonable. I say it's reasonable because obviously you're not having these students take these tests together in a group. They're taking these tests individually. You could also speak to independence between each sample of students is assumed. Meaning that, okay, my friend's in one group and I'm over here in this group. There's nothing that we can do to kind of affect each other in terms of how well we score. Or you don't have one student who is in both classes. There's independence between the two groups of students, the two samples of students. I should say each sample of student. Why am I concerned about my English? English is just a made-up language. It is. All language is made up. It's make-believe. I don't know. Back to this. Now, talked about independence, talked about randomness. I think it's safe to say that 44 and 44 are less than 10% of student population. I think it's safe to say that. I think that if it's a school, let's say, they didn't say where, but I'm assuming it was in the inner city because they did say often in inner cities. But even in a school in the suburbs, let's say, there's way more than 440 students. The only way that it would be not less than 10% is if you lived in like a podunk town with 50 people. Just say. You ever meet somebody who was like, I was valedictorian in my class. How many are in your class? 8? No, but literally, like that's happened to a lot of people, you know? How many are in your class? 230, so okay. That's cool. I graduated with 700. It's ridiculous. Silliness. I run into people who I graduated high school with, and they're just like, oh, hey, and they're like talking to me like they know me, and I'm literally like, I have no idea who you are. Anyway, back to this. Okay. I don't have to have a large enough sample because this is t-testing. However, we do need to talk about the nearly normal condition. What's the problem with talking about the nearly normal condition? There's a huge glaring issue with talking about the nearly normal condition. What is it? What is it? We don't have any data. We don't have any data. I'm sorry, let me rephrase. We do have some data. We have the averages, but we don't have the individual data points. We have no way of knowing whether or not the data is nearly normal. The problem itself never, and this is why it's a gift. It is a gift when the problem tells you this. It is a gift when they say, oh yeah, normal distribution. But this one doesn't say anything. So we can't talk about nearly normal. So this is what I'm going to write in the meantime. And we have talked about this in the past. Quote, nearly normal cannot be determined. Nearly normal cannot be determined, but because, this is huge, because 44 is, quote, large enough, we can proceed. Because 44 is large enough, we can proceed. Statistics has very specific rules about whether or not you are allowed to move forward and proceed. And if you don't meet those rules, a lot of the time we kind of just fudge them. That's literally what happens. Yes. Oh, yeah. Absolutely. Number 12. Literally, number 12. Because the sample size was clearly not large enough. It was 6. Crap. Yeah, can't proceed. Can't proceed. In this one, it's like, okay, nearly normal. We clearly can't talk about nearly normal, but because the sample size is large enough, we're allowed. Yeah, and that has more to do with the central limit theorem. Yeah. Weirdness. But that's what these problems do. Think about it. Like when we looked at scatter plots, we talked about whether or not they were, and now for those of you in the chat, you can't see me, but we talked about if they were straight enough. And I put those in quotes. We talked about, oh, is it normal? It's normal enough. Like, we literally just fudge things all the time. But it comes to a point where it's like number 12, for example. I'll go back. I don't want to go back. I don't know if I didn't write it down, but it comes to something with number 12 where it's like, we can't proceed. We can't. We just simply can't. Like, too many things have gone wrong. What went wrong in number 12? We had no idea whether or not it was a random sample. The nearly normal condition was clearly not met. The sample size as a backup was not large enough. There were too many issues. Too many. One issue, maybe. Too many, can't move forward. Cool. This will be a 2-sample t-test. A 2-sample t-test. Now, degrees of freedom. The most patriotic statistic that you will ever see in your life. I wanted to show you something in the textbook. But before I show it to you, just please keep in mind that you do not have to actually calculate this by hand. One might argue that, well, there's 44 and 44. Doesn't that make 88? Why did the problem say 86? It said 86 because of this calculation right here. It said 86 because of this calculation right here. In fact, hold on, let me go back down a little bit. Where is it? There it is. Cool. I'll read you this paragraph right here. The deep, dark secret is that the sampling model isn't really student's t, but only something close. The trick is that by using a special adjusted degrees of freedom value, we can make it so close to a student's t model that nobody can tell the difference. Again, fudging the numbers. The adjustment formula is straightforward, but doesn't help our understanding much. So we leave it to a computer or a calculator, which we will be doing. We will leave it to the calculator. If you're curious and really want to see the formula, look in the footnote. So we look down in the footnote. There's the formula right there. Then there's a little note. Are you sorry you looked? This formula usually doesn't even give a whole number. If you're using a table, you'll need a whole number, so round down to be safe. If you're using technology, it's even easier. Computers and calculators deal with the degrees of freedom automatically. So the problem said 86 degrees of freedom, meaning you could technically do a TCDF, and I'll show you that later. But for our purposes, I'm going to be doing a 2-sample t-test, and it will calculate the degrees of freedom for me, which is nice. 2-sample t. I believe that's all my information right there. 35.62, 9.31. Oop, sample size was 44. 32.48, 9.43, and the sample size was 44. Alternate hypothesis. I'm doing greater than, because the first sample being greater than the second sample would have been my alternative. Pooled. Don't worry about it. Just leave pooled as is. Calculate. Boom. There are the degrees of freedom, DF. They rounded it to 86 in the problem. Again, you don't have to calculate that by hand. But I am interested in that p-value. I am very interested in that p-value. So hold on. I got a p-value of 0.0598. And this is what I'm going to use to come to my conclusion. There is a way of calculating the, quote, t-score, but I'm going to show you how to do. I'll walk you through those steps next time. In fact, yeah, we'll come back to number 28 later. I just want to get to my conclusion before the end of class. So here's my conclusion. Oh, which, by the way, Normally, I write down a bunch of additional information here, like, oh, here are the averages, and here's the standard deviation, and here's the sample size. I already did that like way up here. I just didn't feel like rewriting it. But it's all right there. That's the information that was typed in. And then as a result, the p-value. Now, this conclusion is borderline. It's borderline. Now, I want to talk about the two possibilities here. If we reject, then, which by the way, technically be like, 0.05 is not less than, it's not low enough. But if we reject, then we say there is enough evidence to show certified teachers get higher scores. If we reject, then we say there is enough evidence to show certified teachers get higher scores. If we fail to reject, then we say we'd say there isn't enough evidence, but we would say there is evidence. Or no, I would say there's not enough evidence. I'm going to do that. Yeah, I'm going to do it that way. There is not enough evidence to show a difference. To show a difference in scores. You may have to walk yourself through this, and I'm going to write some other stuff in a moment. But if you do something like this, I bring you back to the truth versus your decision. I bring you back to this. The truth is, or reality, the null is true, or the null is false. But we don't know that. If we reject, and the null is actually true, we reject the parachute, we live, but we don't get to go skydiving, that is a type 1 error. If we reject the null and it's false, then oh, happy day. If we fail to reject the null, saying, the null is fine, or not enough evidence to show otherwise, and the null is actually true, then oh, happy day. But if we fail to reject and we're wrong, then that is a type 2 error. That is saying, there's nothing wrong with this parachute, but then you jump out of the plane and then you die. If we reject the null hypothesis because it's so stinking close, which is a valid conclusion, you can come to that. Again, fudging the numbers. It's not close enough, Mr. Wernicke. I know it's not close enough. But if we reject and we say, there's enough evidence to show that certified teachers get higher scores, when in reality, there's no difference, we make a type 1 error. But then they get more certified teachers, and the scores don't really change all too much. Okay. But if we fail to reject, and we're wrong, there is a direct consequence. If we say there's not really evidence to show a difference, if we're wrong, then it's like they may continue hiring non-certified teachers despite the fact that they don't produce higher scores. That is the worst error. Now, there is something you could potentially do. This is all with an alpha level at 0.05. What if we raise the alpha level to 0.10? What is a direct consequence of raising the alpha level to 0.10? The beta level goes down. Now, we don't know by how much, but it does go down. The beta level would then drop. Now, think about this. Alpha is the probability of making a type 1 error. Alpha is the probability of making a type 1 error. If we raise alpha, we lower beta. Beta is the probability of making a type 2 error. This is a real-life decision right now. What are you willing to do? It's so borderline. It's so borderline that maybe perhaps we should raise our alpha level to 0.10. Oh, but you're increasing your chances of making a type 1 error. Okay, but what are the consequences of a type 1 error? The consequences of making a type 1 error is, well, they're going to hire more certified teachers even though they don't make much of a difference. But the consequences of making a type 2 error is, they're going to hire whoever they want even though they had the opportunity of getting higher scores. What happens to the power of a test in this situation? If we raise alpha to 0.10, then it lowers beta. We don't know by how much. But then what happens to the power? Yeah, it increases because power is 1 minus beta. So that would increase the power of the test. Definition: the power of a test is your test's ability to detect a false null hypothesis. It is your test's ability to catch and to find a false null hypothesis. So what conclusion should you come to? Here's the thing. Because this p-value is so stinking borderline, reasonably, you can come to either conclusion. You can come to either conclusion. If it were hard and fast, like, yes, have your alpha at 0.05, and you failed to reject as a result because it wasn't low enough, you're fine. Write the appropriate conclusion. I failed to reject because 0.0598 is greater than 0.05. There is not enough evidence to show a difference in scores between certified and non-certified teachers. Fine, great. I'm just saying that if this were a real life situation, you would have to weigh the consequences. Weigh the consequences. Because since this is close enough, if I come to this conclusion of failing to reject, there's a chance that I would be falling into a type 2 error. Now, do I know that for real? No, I don't know that for real, but I could. And if I do, that is technically the worst error. So, Mr. Markey, which one is the answer? Technically, either one. You back up your answer with evidence. You write an appropriate conclusion based on the decision that you make. I'm going to talk more about this problem on Thursday. So be on the lookout for that, and I will talk more about the assessment on Thursday. Yeah. If you haven't left a comment in the chat, please make sure that you do so. I will have the chat over there on my phone. No worries. Then we'll get there. Thank you, too. See you guys. Bye. I'm going to sign off on the live chat. See you. Have a good one. Bye. Okay. End stream.